Welcome to the Explainer. Okay, let's dive right into this, because today we're setting the scene for one of the absolute highest stakes moments in engineering. We're talking about waking up a 28,500 horsepower machine for the very first time. This is the first fired start of an aeroderivative gas turbine, and let me tell you, it is an incredibly dramatic moment.
Think about the sheer contrast here. You've got months of slow, meticulous construction, right? Heavy rigging, the careful flushing of pipes, just endless preparation. But all of that immense effort ultimately comes down to a single control room command and a countdown that's literally measured in seconds. It's just a few critical moments of automated, irreversible logic about to unfold before our eyes.
So let's start with Phase 1, the preparation, the PSOR.
You can kind of think of this just like a commercial pilot's strict pre-flight checklist. You'd never push back from the gate without verifying every single critical system. And you definitely don't fire a massive industrial turbine without doing the exact same thing. Electrical interfaces must be completely verified. The integrity of the lifeblood oil systems, that's both your turbine and generator lube oil, has to be confirmed. Fuel quality is checked. The inlet is totally cleared of any foreign object debris. And fire detection must be active. Verifying that oil and clearing out debris, that is absolutely non-negotiable before any metal even thinks about moving.
Which brings us to our next step, the action, waking the giant.
Once that PSOR checklist is fully signed off, we transition straight from static preparation into a mechanical awakening. The control room watches this exact automated sequence play out. It moves from the sign-off to the starter physically cranking the engine, right into a strictly timed ignition window countdown, and finally, if all goes according to plan, into a stabilized idle warm-up timer.
2,200. Now this machine cannot just start itself. The hydraulic starter has to physically crank this massive engine rotor to roughly 2,200 RPM. And you might be wondering, why so fast? Well, because you have to establish a massive amount of internal airflow before a single spark or a single drop of fuel is ever introduced into the system. Basically, it needs to breathe first.
And that leads us to the most tense moment, the climax, the ignition window.
The tension really builds in the control room as the igniters finally spark and those fuel valves fly open. But here's the thing, the engine doesn't just assume it worked. The system shifts its focus entirely to a strict set of logic to visually and thermally confirm combustion. Actually, I want to halt our momentum for a second and ask you a really critical question. What if the igniters are sparking and the fuel is actively flowing, but the temperature hasn't risen? Think about the massive danger there. You are pumping highly combustible, completely unburned fuel into a hot, pressurized combustor. If it hasn't lit, that fuel is just accumulating.
Well, the answer to that nightmare scenario is the auto abort. It's a built-in, automatic safety protocol. The system doesn't just cross its fingers and hope that it lit. It demands hard proof of real combustion, specifically via a rapid rise in the turbine inlet temperature. If it fails to see that proof, it immediately triggers this failsafe to cut the fuel and shut the whole attempt down. It does this rather than blindly trying again and risking a catastrophic fuel accumulation.
And there are exact ticking clock time limits that the system allows for that temperature to rise before the auto abort completely takes over. If you're burning gas fuel, you have roughly 10 seconds. That's it. If you're burning liquid fuel, you get 25 seconds. It is a precise, highly unforgiving window. Miss it, and the system shuts you down.
The entire philosophy here boils down to this: controlled, not rushed. This incredibly controlled, incremental startup exists precisely to catch fatal problems, like a fuel issue or a bad sensor fault at low stakes. You absolutely want to catch a failure to ignite right now, in this strict window, before the unit ever faces the extreme mechanical and thermal stress of a full operating load.
Which brings us to the final part of today's overview, the cliffhanger power ascension preview. Okay, take a breath. If the temperature did rise, the tension in the room is finally relieved. The engine is safely lit, the fire is blazing, and it's comfortably idling. But to actually make power, you have to apply load. And you do this in gradual 5 megawatt stair steps. You add load, and then you hold. You do this to prevent severe thermal shock from rapid temperature swings across the hot section. You literally have to let the temperatures and the mechanical vibrations completely stabilize before you ask the machine for even a little bit more power.
Which brings us to a final, pretty provocative thought.
Now that we have a blazing fire, a spinning turbine, and we understand how load is gradually applied, how do we actually test the safety systems to prove they won't overreact to a single minor fault and shut the whole shebang down the moment we finally connect to the electrical grid? Well, that is exactly what we're going to uncover in Part 2.